the instantaneous rate of change, or the IROC. The IROC is the slope or difference in y value or rate of difference of change at a specific point on a function. So what we're looking at is a rate of change at a specific point in the function, or an instantaneous rate of change, and it will be the change in y values at a specific point. So whether at a specific point the function is increasing or decreasing by a certain value. So it is calculated by a small increment change in the x value, or plus or minus 0.001, which I, in this case, use plus 0.001. So we see the equation is f a plus h minus f of a over h. It is like this equation, y2 minus y1 over x2 minus x1. However, the denominator, the change in x, will always be 0.001. And the equation here is calculated like the average rate of change. However, at such a small rate, or such a small change in x, it's almost instantaneous. So we see here that you're going to have something that looks like this. However, your difference in the value here is 0.001. So your output from that will be very slight difference from this. And you calculate it like this because it's such a small difference in the x value that you'll have almost an instantaneous rate of change, or an instant point at where the y values are changing. So a tangent line represents the slope or change at a specific point on the function. It only touches one point of the function. So see here, I have a cubic function, and say we try to find the tangent line. Let's say that's at -4 for x. We see that this tangent line here will only meet that point, and this, you can calculate the slope of this line, and it will be your instantaneous rate of change. So to find a point where there's a positive IROC, I looked at the graph, and I could see that when x equals 20, the graph seemed to be increasing. So what I have here is I plug in my values to my equation. I have f of 20.001 minus f of 20 over 0.001. So we go over to the side to do our calculations to see what this equals. So we plug in 20 into our original equation, and we come up with a number of 12.0109589. Now we do the same thing for 20.001, and what we find out is that we come up with a number of 12.00 or 0.114424. We then subtract this number from this number, and then divide a point 0.001. What we find is that we have a change of 0.4835. And what's interesting about this is that it is very close to the equation of our asymptote. And this is because when x is equal to 20, the function is approaching the line of the asymptote, and therefore the equation of the slope is very similar to it. And we could look at that and expect that before coming into this by seeing on the graph how it is closing in on the asymptote. Therefore, the equation must be very similar. So we can look graphically and find a point where x is, when the function is negative. So I looked at the graph and saw that when x is equal to 2, it looked like that the function was decreasing. So again, we plug in our values, and we have f of 2.001 minus f of 2 over 0.001. We go over here to find out what those values are. When we plug in 2, we come out with -2.5. And when we have 2.001, we come out with -2.0 or 2.50381651. So what we do is we subtract the numbers again, and here you'll have addition. We come out with -3.81651. So if we look at our graph, when x is equal to 20, which is about this point right here, we see that we would have an oblique asymptote running along here, and we see that this point on the function, that the function is increasing at a very similar rate to the asymptote, and we see that as increasing. Here at x equals 2, we can visually see that the quadratic, or this quadratic shape right here, the function is decreasing as the y value